All right, we are now recording. Well, that's 6:30, and we have had some more come in. Let's see. Well, we might as well get started. Others are coming. I'm really impressed with how many people are coming in just one 100-person class. Good. So hopefully on your screen you can see the old exam here on the right, and I've got ChemDraw open on the left. I don't have a stylus or a pen or anything like that, so I'll have to do everything in ChemDraw, which might take a little bit longer. But let me copy this in. Let's do change settings. So this first question I actually don't really like all that much, because I'm asking here for the hybridization and the geometry, and really they're kind of the same question. I think a better question would just ask for the hybridization. But as we've discussed in class, there's really only three hybridizations that you need to be concerned about: SP, SP2, and SP3. Those are the only ones we're going to run into. Someone came up after class today and asked about like T-shaped and octahedral. No, those require d orbitals. We're never going to run into those. Those are for transition metals. So remember that the way you know when an atom is sp3 hybridized, to put it the simplest way, this may be an overgeneralization, but is if there are only single bonds, then the atom is sp3 hybridized. Probably. There are exceptions. I'm here talking about atoms that have a zero formal charge, of course. Once we start getting into formal charges, then hybridizations can change. And sp2 hybridization brings with it a double bond. And sp hybridization brings with it either a triple bond or a molecule of the carbon that has two double bonds coming off it, like in CO2. So the carbon atom in CO2 is sp hybridized because it has two double bonds coming off it. So this arrow is pointing to this atom. I see only single bonds coming off of that carbon. That makes it sp3 hybridized. In terms of the shape, tetrahedral. So you only put the shape if it asks for the shape or the geometry. If it just asks for the hybridization, just put the hybridization. But it really is the same question, because all sp3 hybridized atoms are also tetrahedral. So that's why I didn't really like this question, now that I think about it. This arrow is pointing to this carbon, which has a double bond coming off it, so it must be sp2 hybridized. And really, I should be doing this. It just takes a little while. Here we're pointing to another carbon atom that has only single bonds. So this one is going to be sp3 hybridized. Here again, we have an atom that has a double bond. So sp2 hybridization. And then finally, this carbon atom is involved in a triple bond, so it's going to be sp hybridized. Should be fairly straightforward. The next compound is a bunch of functional groups, and so we'll be identifying functional groups. First of all, how many hydrogen atoms are in compound A? Well, we can count. 1, 2, 3, 5, 7, 9, 11, 13, 15, 17, 19, 20, 21, 22, 24, 26, and lastly, the one in the nitrogen makes 27. So I think 27 is the best answer over here. And then we come to identifying functional groups. So trying to think about the easiest way to do this. These are both going to be alkyl halides. Though I'm sure I accepted aromatic halide, I'm sure I accepted aryl halide. There are other ways to put it. But those are going to be alkyl halides. Really, we should include the carbon atom. So maybe I want to do more like that. And then we also have two aromatic rings. Here's one. And here's one.
Could we also call them benzene or arine?
Those are also, well, I don't know about benzene. Benzene's the name for the actual compound.
Oh, gotcha. Okay.
Arine is certainly fine.
Arine? Okay. That's good.
One of the things I've noticed over the years is that organic chemists seem never to be happy until there's at least two different words for any given one thing. I don't know why that is. And then we've got some nitrogens in the next ring. Those are going to be amines. Remember, amines are organic derivatives of ammonia. And so it's a nitrogen with at least one alkyl group attached. And now I can use the term alkyl group since we've defined it. So these are both tertiary amines, meaning there's actually three alkyl groups attached, but you only need one. 1, 2, or 3 is fine. The only thing that's not an amine is NH3 itself, which is ammonia. Ammonia is inorganic. And then over here, we've got an oxygen attached to two carbons. Remember, that falls under the definition of an ether. And there's just one functional group left. It's this nitrogen next to a carbonyl. And that's not an amine any longer. That's an amide. So an amide is a nitrogen next to a carbonyl. Just like a carboxylic acid is OH next to a carbonyl. An ester is O-alkyl next to a carbonyl. So there's lots of different carbonyl-containing functional groups. Aldehydes have a hydrogen attached to the carbonyl carbon, and ketones of two alkyl groups. And I'm probably forgetting one or two. So there's lots of carbonyl-containing functional groups. So it said to label any three of those that are different. So those are among the acceptable answers. So far, so good. And you can always look at the answer key too. On the next page, we have some questions about acids. So you'll notice in the first question, it does not give pKa's. That's because you don't need them. The most acidic compound, I think, is fairly patently obviously HBr. We know that's a strong acid. The next most acidic compound is going to be the carboxylic acid. So you need to know that carboxylic acids are the most acidic organic species, at least among the ones we're going to run into. There are some weird compounds that are more acidic, but I don't think we'll ever run into one of them. So that means, okay, least acidic to most acidic. So most acidic is 1, is going to be HBr. Then 2 is going to be the carboxylic acid. And then you have a choice between an alcohol and a terminal alkyne. And in the alcohol, the hydrogen is attached to an electronegative oxygen. That means that if you remove the proton, if a strong enough base pulls off this proton and you get O-, the minus charge is at least on an electronegative atom. If you take a strong base, and it'll take a really strong base to pull off this proton, although it is possible, that will put the minus charge on the carbon, and carbon is significantly less electronegative than oxygen. So I think the best answer is the alcohol being number 3 and the terminal alkyne being number 4. Let me know if I'm going too fast, by the way, or since there's only, oh, wow, we're up to 10. Let me open chat. I never really know where to put chat. I guess this is as good a place as any.
Can you explain what you mean by terminal when you talk about terminal?
Well, I accidentally used an organic 2 word, but I mean that the triple bond is on the end of the molecule, as opposed to being in the middle of the chain. The terminal alkyne is a CH bond. So that's what that means.
Okay, thank you.
Terminal alkyne, internal alkyne. I'm mostly concerned that you guys know what an alkyne is at this point. We'll get to terminal alkynes in chapter, golly. Well, actually, I lied. It's not an organic 2 term. We'll get to them in chapter 9. So we'll see them this semester. Okay, there are probably at least a dozen isomers of C5H11Cl. There was a misprint originally on the exam. It said C5H12Cl. It should say C5H11Cl. And all you need to do is put together 5 carbons with a chlorine. So this is one of them. Whoops. This is one of them. You've got 1 chloropentane, 2 chloropentane, and 3 chloropentane. And that's already 4 of them. I'm sorry, that's already 3 of them. And then you can start moving around methyl groups. You could come up with something like this. That would be C5H11Cl. Let me make sure. 1, 2, 3, 4, 5. Yep, that would be one of them. This would be one of them. One, two, three, four, five. This is one of them. I think you guys get the idea by now. There's lots and lots of correct answers. Any four of them would have been fine. And then finally, we have a question about formal charges. And cross out any configurations that are unreasonable. The first one's unreasonable. Boron shouldn't have a lone pair. Boron is one of the exceptions to the octet rule. It is only 6 electrons around it with a formal charge of 0. The next one is just fine. In fact, we drew a molecule like that, CO2. And the carbon is a formal charge of 0. So that one we would leave alone. The next one is nitrogen with 4 bonds and no lone pairs. So that nitrogen has a formal charge of +1. And you can verify that by using that formula. What is it? The number of valence electrons on the free atom, which is 5, minus half the number of electrons in bonds, or minus the number of bonds. We've got 4 bonds. 5 minus 4 is 1. Minus the number of non-bonding lone pairs, which there's none. So the formal charge is +1. The next one is nitrogen with 5 bonds, and that's not a reasonable configuration. Nitrogen cannot violate the octet rule. The next one is carbon with 4 bonds, which is good. 2 single bonds and 1 double bond. That's totally fine. And it has a formal charge of 0. Next one has bromine with 2 bonds and 2 lone pairs. And that actually is okay. To figure out the formal charge, we'll use that formula. Number of electrons in the free bromine atom is 7. Valence electrons, 7. Minus the number of bonds is 2. 7 minus 2 is 5. And then minus the number of electrons in non-bonding lone pairs, which is 4. 5 minus 4 is 1. So this atom will have a formal charge of +1. You don't see bromine like that very often, but it is allowed. Bromine would much rather have a minus charge than a plus charge and be a bromide ion. Next one is oxygen with 4 bonds. That's no good. That's not a reasonable configuration. The next one is hydrogen with 2 electrons. That's called the hydride ion. Hydride. So it's not H+, it's H-. And so this one will have a formal charge of -1. Next, we have a carbon atom with 3 bonds and 1 lone pair. And you can calculate the formal charge. The number of electrons on the free atom is 4. We subtract from that the number of bonds, which is 3. 4 minus 3 is 1. From that, we subtract the number of electrons in non-bonding lone pairs, which is 2. And 1 minus 2 is -1. So this carbon is a formal charge of -1. As does the next oxygen. This oxygen has 1 bond and 3 lone pairs. We put that in the class notes. The formal charge in an oxygen with 3 lone pairs and 1 bond is -1. And you can verify that using the formula. Next, we have oxygen with 3 bonds and 1 lone pair. And that oxygen is going to have a formal charge of +1. That's an allowed configuration. The central oxygen in ozone looks like that. And after that, we have a carbon atom with 2 bonds and 2 lone pairs. That's no good. The carbon atom would have a formal charge of -2, which is not allowed. Make sense? So this, I think, was mostly chapter 2 stuff. Let's look at the next page. Moving right along. Yes, let's move them. We'll see what happens. Next, we need to name these compounds. This one is going to be named as a cyclopentane. The methyl groups take priority over the propyl group. So there's 2 methyl groups on carbon 1 and 1 methyl group in carbon 2. So carbons 1, 1, and 2 have methyl groups, and then there's a propyl group in carbon 2. So I think the best name would be 1,1,2 trimethyl. Two propyl cyclopentane. I think that's the best name. Again, the methyl groups take priority over the propyl group because they come first in the alphabet. This one over here looks like we've got a 1, 2, 3, 4, 5, 6, 7, 8, 9 membered carbon chain. So this is going to be named as a nonane. And which side is the first branch point? I think this end is closer to the first branch point. So we'll start numbering over here. So that's the numbering system we'll use. We've got 2 methyl groups in carbon 3 and an isopropyl group in carbon 6. Remember, the iso and isopropyl doesn't count for alphabetization. It's a silly rule, but we're stuck with it. So the methyl groups again come first. So we've got 3,3-dimethyl, 6-isopropyl, nonane.
I have a question about the isopropyl.
Yes.
So, so is it like when it looks like that, is that how we know it's
Yes, because the connection point to the propyl group comes on the middle carbon. That's how you know it's isopropyl. If the connection comes on the end carbon, then it's just propyl.
Okay, I see. Thank you.
Yep. Next, we need to, and by the way, once you know how to name alkanes, you know how to name alkyl halides too. You just need to know fluoro, chloro, bromo, and iodo, which are all pretty straightforward. So we need to draw 1,1,3 tribromo 3-ethyl hexane. So let me put in a 6-carbon chain. And next we need bromines on carbons 1, 1, and 3. And then also 3-ethyl. On this first exam, let's be careful with our lone pairs. In future, lone pairs will matter the most when you're dealing with an atom that has a non-zero formal charge. Atoms with a non-zero formal charge, we can usually let the lone pairs go, unless you're using them in a mechanism, let's say. If you're using them with arrow pushing, then you need to show them. Best rule of thumb is when in doubt, show the lone pairs. It's never wrong, and it takes just a couple of seconds. So that's how that compound would look like. Next, we've got a very highly resonance stabilized cation. And you can use arrow pushing to help yourself find other resonance forms. For example, we can move that pi bond over. That would give us this. Put the plus charge over there. We could, this is kind of bad form, doing two arrows in the same structure, but we could also have moved that one over. That would give us this. We could get another resonance form by moving this pi bond over. And there's lots of others. We could move this bond over here. We could have moved this bond over here. We can move both these bonds. There's lots of other resonance forms.
From the original form, could we just possibly shuffle a double bond in just different areas of those two rings, too?
Well, technically, I guess I would have had to accept that.
So you want to, okay, sounds good.
But I probably was grumpy about it.
Okay, sounds good. Because like what I mean by that is if we just shuffle the double bonds around.
Yeah, I know
like,
what you mean, to the other resonance form of the benzene ring.
Yeah, that way we won't have to deal with any of like the formal charge or like the charge.
Well, since they needed to do three of them, they needed to do it at least once. That's probably
Okay.
why I phrased the problem like that, to force them to do it at least once.
Gotcha.
I don't remember if anyone just thought of using the other resonance form of the benzene ring. Probably they did. But there's lots of resonance forms. So remember with resonance, what you're looking for is three atom groupings that consist of a double bond next to an atom that's sp2 hybridized. And you get the other resonance form by switching the double bond with whatever the situation is on the sp2 hybridized atom. And remember, we move the electrons from the electron-rich place to the electron-poor place. So moving this double bond over gets rid of the plus charge. That carbon now has a formal charge of 0. And since we took electrons away from this carbon, that carbon now is the one with the formal charge of +1. So there were lots and lots of correct answers to that question. Next, we have some acid-base questions. And I'm sorry, but I'm just going to have to excuse myself for 30 seconds. I just have to run to the back. By the way, you might see a cat later. All right, back we are. So the first one is showing an acid-base equilibrium. And here I'm giving the pKa's of the two acids. Now remember that the equilibrium always favors the side of the weaker acid. What that means is the thing that has the the higher pKa. Remember, the higher the pKa, the weaker the acid, the lower the pKa, the stronger the acid. So the side of the equation that has the higher pKa will be favored. That means this equilibrium is going to go from the right to the left. And the reaction will proceed by this species reacting with this species, which happens to be called benzoic acid, to give the alcohol and the benzoate ion. So that's very important for you to know. The equilibrium always favors the weaker acid. That means that the reaction will go towards the side with the higher pKa. Always. There's no exceptions. Now, in terms of acid strength, let's compare these two pKa values. We already know that the lower pKa is the stronger acid. But another thing you need to know is that the pKa scale is logarithmic because it's minus log of the equilibrium constant. That means that every unit of movement in the pKa scale represents a factor of 10. So this acid is not 4 times as strong as this one. It's 10 to the 12th times as strong. It's 1 trillion times as strong. So acid Y is 1 trillion times as strong as X. That's the best answer. So remember that the pKa scale is logarithmic. That's definitely a thing you'll need to know for the rest of the year. And we already said the equilibrium lies to the left. And now we're being asked to draw the mechanism of the reaction. So I'm just going to copy these. So remember, when you're drawing the mechanism, the arrow always starts at the base, always. There are no exceptions. So the arrow goes from the base to the hydrogen and pulls the proton off of whatever atom it's attached to. And then you break the bond from the hydrogen to whatever that atom is. In this case, it's an oxygen, which is electronegative. And you get the benzoate ion and the alcohol. So that's the best way to draw the mechanism. Always remember, arrows are only used for movement of electrons. You need to. Electrons are
Dr.
only used for movement of electrons, never of atoms. I'm sorry.
Dr. Watt.
Yes.
Yeah, the original mechanism, what you have on the right was the before the reaction progressed, I believe.
What
Or,
I have, but the reaction goes to the left. That's why I switched
oh,
sides.
that's right. That's right. Yep, gotcha.
Yeah. So that's why I switched sides. We needed to show Y and Z reacting to give W and X. And so again, the arrow starts at the base, always. There are no exceptions. The arrow will start at the species that's electron rich. And what this arrow means is that an electron pair from the oxygen is coming out and grabbing the proton off of the acid. And then this arrow means that we break the oxygen-hydrogen bond and put the electrons onto oxygen. So this oxygen now is a minus charge. And this oxygen now is a charge of 0. So that's how to draw that mechanism. Next, we have a Lewis acid-base reaction. The arrow will still begin at the base. So we start it at the Lewis base, which is the electron-rich species. And we draw it toward the electron-poor aluminum atom. And so we're going to have a new bond between nitrogen and aluminum. And this arrow here means that the lone pair on nitrogen is going towards the aluminum atom to form a bond between nitrogen and aluminum. So the aluminum's over here. I think I hear my cat scratching at my door. Methyl groups all around. And if you work out the formal charges, the nitrogen will have a formal charge of +1, and the aluminum will have a formal charge of -1. Something to notice, by the way, which you hopefully learned in Gen Chem, is that charge is always conserved in every reaction, always. So the overall total charge over here, for instance, is -1. The total charge on the other side of the equation is also -1. Over here, the total charge is 0 on this side of the equation. Here, the total charge is still 0. +1 and -1 equals 0. So that's another thing to look for to make sure your equations are balanced. You want to make sure that charge is conserved on both sides of the equation.
This
Good.
might sound like a dumb question, but the way how you drew the arrow on that bond, could we draw it curved up? Like I'm just once
Certainly.
again, certainly okay. Because I was told that we had to draw arrows like a certain way, like rather than just so we could also draw it curved up. Okay.
Either way.
Sounds great.
That's another example of not only would I not take off points, but I wouldn't even notice. I would notice if the arrow is going in the wrong direction, or if it starts and ends in the wrong place. But minor differences like that don't matter. They're the same thing. Actually, I could find fault with this arrow. I would have liked it to go a little further and almost touch the aluminum. But yes, that's completely acceptable. This is going much faster than I expected. I might have to make up some problems. All right, consider the molecule cis-1,3-dibromocyclohexane. Draw the flat structure in the box to the right. So you'll just draw a normal hexagonal cyclohexane. And you want cis-1,3-dibromo. Now I'll turn the question back on you. There may be a couple different answers to this. What would I not only not have taken off points for, but not even have noticed?
The lone pairs?
Well, I might take off points for lone pairs on the first exam.
Okay. If we place the BRs in another direction, in another like
Another place, yup, that's fine. What else?
if we also instead of the wedges, we drew the dash.
Bingo. That would still be cis if they were both dash bonds. Either both up or both down.
Both up with what you drew, right?
Right, I drew them both up, but both down would also be fine. So now draw both chair conformations. I'm going to make you very jealous. I can draw a chair cyclohexane in one mouse click. So we could put the two bromines. Maybe I'll put the first one here, though I certainly don't have to. That would mean the second one goes here. Oh. Sorry, I just realized something, which is pretty minor. And since the question says, be sure to show all hydrogens directly attached to the cyclohexane ring using the correct bond angles. That's why I'm adding them all. If it didn't say it, I wouldn't have had to do it, but it does say it. So that's one chair. In the other chair, we'll move this carbon down and this carbon up, just like we did in class. The bromines will still be up, but the one on the right will be over here. So the bromine on the right will be over here. still pointing up, and the bromine on the left will be over here. Let me add my lone pairs just to make it official. And hydrogens elsewhere. Did I get them all? I think I did. So in this conformation, the two bromines are axial, and in this conformation, they're both equatorial. So remember that because of 1,3 diaxial interactions, substituents prefer to be equatorial. And in this one, they're both equatorial. In the trans compound, you'd have at all times one axial and one equatorial. So they would be the same in energy, since they're both bromines. Both groups are the same. So that means that the one that's lower in energy would be this one. Next, draw a Newman projection. That will take me a while in ChemDraw, so maybe it's good that we have so much time left. There's a reason I'm putting CH4 here that will become evident eventually. That looks really funky, but I might be able to change that. Text, centered. Maybe flush right would look better. Flush left looks best. Oops. I screwed up this one. This is definitely not my greatest Newman projection ever.
Normally Newman projections I thought were to be like one circle. So I'm gonna ask why it's two this time.
The reason it's two circles is because we're looking down two bonds at the same time. This one
Uh-huh.
and this one, because those two bonds are parallel.
Wait, let me see.
Hexane Newman projections have two circles.
Isn't that like the same for every other chair confirmation? Like parallel or bond?
Yeah. We're looking down two bonds at the same time. So cyclohexane chairs in the Newman projection look something like this.
Wait, if it's like a cyclo kind of thing, would that involve two circles
It
or
depends
like if it's like
on which cyclo compound, but cyclohexane is two circles
so
because
okay,
those two bonds are parallel.
is cyclohexane always two circles for Newton projections?
For
Always?
chairs,
Yeah, for chairs.
yes. Yeah, there's no avoiding it.
Okay. Okay.
So let me see where my bromines are going to go.
We have also drawn it like a different way rather than like if you picture it like that, if you
I had the
think
wrong
let's say
bonds.
that front carbon, I was gonna ask, could we also draw it in which it's like two branches going diagonally upwards and one branch is going straight down rather than two branches going diagonally downward and that one branch going straight up? Could we also draw like that? That the front carbons on both of those circles.
You can switch the front and back carbons, yes.
Okay. So there is multiple ways to draw this. Just
Oh,
not the one.
yes.
Gotcha. Okay.
I'm going to put the bromines on the back carbons. But this is by no means the only correct way to do it. One thing I would say about drawing cyclohexane Newman projections, leave these two positions as CH2s. Don't put anything on them. Turn the molecule whichever way you need to so that those stay as CH2s. Because otherwise it's impossible to tell whether something's equatorial or axial. So turn the molecule however you need to. That should always be possible. I think it will always be possible. Yeah, whether it's 1, 2, 1, 3, or 1, 4, it's always possible to leave those as CH2s. So, yeah, I didn't do the best job in the world on that Newman projection, but it's acceptable. They're kind of hard to draw in ChemDraw. Any other questions on the cyclohexanes? So 1-bromopropane. This is really just like butane. Only instead of a CH3, you've got a bromine. And here we go with Newman projections again. So the lowest energy Newman projection is going to have the bromine and the methyl group. And the way you know it's on the end is, remember, the two CH2s are going to be the two carbons that are represented by the circle in the Newman projection. We're looking down that bond. So one carbon will be the CH3 and one carbon will be the bromine. And you could put either the methyl or the bromine in front, doesn't matter. I think I'll put the methyl group in front. And the lowest energy conformation will have the methyl and the bromine anti to each other. So that's the lowest energy conformation. The next lowest energy conformation will be the Gauss conformation. And this is not the only correct way to draw these. So the two staggered conformations are the lowest in energy. The next one will be the methyl hydrogen eclipsed conformation. Which, just as the name implies, will have I don't know if it's going to let me do it. So I'll just kind of put an H in space over here. Covering it with red ink. But that's the methyl hydrogen eclipsed. And I don't think I have room for the lone pairs. And the highest energy of all will be the methyl bromine eclipsed. Now I'm drawing them in this order because the question says to draw them in order from lowest energy to highest energy. If it didn't say that, then I could draw them in any order I wanted to. But the question specifically says to go from lowest energy to highest energy. So that's why I drew them in that order. Good. So the Gauss conformation is B, and the methyl bromine eclipsed conformation is D. Then it says to do the Newman projections for propane, which is just like ethane. Actually, I'm going to borrow this. So there's propane. It's just like ethane, except it has an extra methyl group. And you can put the methyl group in front or in back. Either way is fine. That's going to be your staggered conformation. And I'll take what have I done? Let's undo. And all we need to get the eclipse conformation of propane is change the bromine to a hydrogen. And that's the eclipsed conformation. Oh, I see the problem. Why is that not copying it? Fine, I'll draw another Newman projection. There we go. There's your eclipse confirmation. Hopefully this is making sense so far. I actually don't have room to put the sawhorse projections. So here's what I'll do. So first we'll do the staggered conformation. That's going to have the bonds like this. That's staggered. And then our eclipse conformation. Whoops. Will look a little something like that.
So wait, for staggered confirmations, would it be like evenly, like both sides will look the same, while for eclipse, both sides look a bit different, or no, they
I'm
still
not
look
sure what you mean. To me, it looks kind of the opposite of that.
Sorry, what I mean is that how would I wait, sorry, give me 1 second. I need to observe.
Because
Almost like
in the staggered conformation, this methyl group needs to be between the two hydrogens, just like it's between the two hydrogens in the Newman projection. And in the eclipse conformation, the methyl group and the hydrogen are directly in front of and behind each other.
oh wait. So for staggered, methyl group is between, and then in eclipsed. How does the eclipse sawhorse projection show that the CH3 is right behind an H?
Well, it's tricky to do in the Newman projection. You just do the best you can. But this CH3, I chose to draw the CH3 straight up. I didn't have to. I could have put the CH3 over here or over here.
Okay.
So I put this hydrogen straight up. So the CH3 and the H are directly in front of and behind each other in the eclipse conformation.
Okay, kind of makes sense. Kind of makes sense. Kind of makes sense. Yep.
So as with so many things, this is not the only correct way to do it. There's a multitude of other correct ways. This is just how I felt like doing it at the time. Other questions on conformations?
But is that the same way how you draw the saw force projections for all kinds of molecules? Like for the staggered conformation, one would be between two hydrogens, and then let's say if one's right behind another, they'd both be pointing up, both be pointing down, or just like the way how you drew it right there.
I think you're getting thrown off by whether it needs to look exactly like that. Let me draw you another eclipse conformation.
Okay, cool.
Equally acceptable. I'll even put the methyl group over here. That's also eclipsed. You can tell because the methyl and the hydrogen are directly in front of and behind each other.
I see. So
you can see those two hydrogens are directly in front of and behind each other.
I got you. So basically, it's just the same. It's just a CH3 and an H just goes in the same direction, correct?
Right.
And that would also be eclipsed.
Yes.
And then for the staggered conformation, they're not going in the same direction. They're just as long as it's between two hydrogens, like how you said, right? Can I possibly
you can see that in the Newman projection also.
wait? So wait, it's not like can you see this little arrow, like this marker? I'm not gonna draw anything. Can you see it?
No.
Oh, that's weird. Yeah, wait, hang on.
I don't think you can draw on my screen.
I can't. Darn. Okay. But I think I get.
I don't think so.
Yes.
It's possible, but it would be news to me.
Is that? Can you see it? I'm drawing something.
No.
Okay. Yeah. Then never mind. But
you circled a hydrogen.
Oh, okay, so you can see my drawing. Yes. Nice. Okay, but I get what you mean now. So sounds good.
Okay. So this one says to draw the products of the Bronsted-Lowry or Lewis acid-base reactions. This is always good practice. It doesn't say to do the mechanisms, but I'm going to do the mechanisms since it makes it easier to see. In the first one, we start the arrow at the base. That's always true. And we point the arrow towards the acid, which is going to be the boron atom. This is a Lewis acid-base reaction. Oops. And the final product is going to be a boron with 4 chlorines. The boron will have a minus charge. You can verify that using the formula for formal charge. Boron with 4 bonds and no lone pairs is a formal charge of -1. I think it's safe to say that boron should never have a lone pair. I've never, ever seen that. So that's what the product should look like. In this case, hydride ion is our base. I'm just going to move it over here to make it a little easier for me. The hydride's the base. You can tell because it is a minus charge. And the hydride's going to pull the proton off of the phenol, which is benzene ring with an OH group. And so the final products are going to be benzene with O minus, and again, I want to stress they did not have to show the mechanisms on this exam. I'm just doing it because I think it makes it easier to see. And the other species is just H2. Let me explain these arrows since I think that students struggle with mechanisms. So this arrow here means that the lone pair on the hydride ion, H minus, is reaching out to pull H plus off of this OH group. And then this arrow over here means that we're breaking the oxygen-hydrogen bond and putting the electrons onto oxygen. So you go from oxygen with 2 lone pairs to oxygen with 3 lone pairs and a minus charge. So these would be the 2 products you'd get out at the end.
Why can't we show the hydrogen that's going to the other one, like from the arrow to the hydrogen on the benzene ring one to the one on the free one?
The reason you don't draw the arrow in the other direction is because arrows are only used to show movement of electrons, not of atoms. So you should never use an arrow meaning this H goes here. Remember the rule for arrows. They have only one rule. And that is that electron starts here. The electron pair starts at the tail of the arrow, and the electron pair ends at the head of the arrow. That is always going to be true, always. There are no exceptions. So you always use the arrows to show movement of electrons, never of atoms, never of charges. Why is it that way? I don't know. That's just the way the formality was devised. Mechanisms are a relatively recent thing in organic chemistry. I don't think people drew too many mechanisms in the 50s. So I don't think I'm really answering your question, but I'm afraid that's the best I can do. Did I at least understand your question right?
No, yeah, you explained it. Thank you.
Yep. So,
Instead of H dash H, would it be okay if we could just put H2? Is that something you wouldn't mind, or?
no, I wouldn't mind that.
Okay, gotcha.
The reason I don't like answering questions like that is I've just made a promise and now I have to remember it.
Sorry.
It's really up to the graders, but I'm sure the graders would accept that. So in the next one, we have a nitrogen base, nitrogen with a minus charge. So this is going to be our base. You can tell that, you know that because nitrogen with a minus charge is a very alkaline species, very strong base. You don't often see nitrogen with a minus charge. So that's going to pull the proton off of the alcohol. That's a strong enough base to deprotonate an alcohol. And so the mechanism would start the arrow at the base and end the arrow at the hydrogen. And then we have another arrow breaking the hydrogen-oxygen bond and putting the electrons onto oxygen. And of course, these arrows could go underneath also. Not only would I not take off points, I wouldn't even notice. That means you need to practice until you also don't notice, until you just see them as being the same thing and are confident about that. So this hydrogen that's on the alcohol is going to wind up on the nitrogen. And now this oxygen on the that was on the alcohol is going to have the minus charge. So that's going to be how the nitrogen will look. It gained a hydrogen because it pulled the proton off of the alcohol. Let's see if it will let me do this. I forget how smart, ChemDraw's not smart enough. And I think you can see why lone pairs are especially important when an atom is a non-zero formal charge. It's just clearer what's going on. So it's not an arbitrary rule. It's something that's meant to clarify. So those are the two species that you would get. Notice in all Bronsted-Lowry acid reactions, you're going to have a hydrogen moving from the acid to the base. There are no exceptions. And the arrows always start at the base. Now, I could have shown them the mechanisms. I didn't, but I could have. That might have made the questions a little easier. But you can see in the instructions that the instructions don't say to draw the mechanism, so they didn't have to. They just needed to draw the products. I don't remember how many people drew the mechanisms. It was 4 years ago, after all. Next, we have this species and this species. Now, how do we know which is the acid and which is the base? Well, this compound is a carboxylic acid, so probably that's going to be an acid. This compound is ammonia, and we learned in Gen Chem that ammonia is a weak base. So the ammonia is going to act as a base, and the carboxylic acid is going to act as an acid. So remember, the arrow always starts at the base and goes to the hydrogen on the acid. Then we break this oxygen-hydrogen bond and put the electrons onto oxygen. So what we get out of it is the acetate ion whoops. So there's the acetate ion. And I'm sure I would have accepted it if they just drew NH4 plus. Or if they drew it out, a nitrogen with 4 hydrogens and a plus charge in the nitrogen, either is fine. Then, last but not least, we've got OH minus over here. That can be either a Bronsted-Lowry base or a Lewis base. On the left-hand side, we've got a carbon with a plus charge. That's called a carbocation. And a carbocation is missing an electron pair. So that's why the carbon is a plus charge. Carbocations are very good Lewis acids. The way you know that is because it's missing electrons. So anything that wants an electron pair is going to be a Lewis acid. By definition, that's what a Lewis acid is. Something that's an electron pair acceptor. So our arrow is going to start at the Lewis base and end at the Lewis acid. Something like that. And the result is going to have a new bond between the carbon and the oxygen. And let me see if I can do this. That is the new bond we just formed. It used to be an electron pair with the minus charge on oxygen. And then we used that electron pair to form a bond to carbon. Once we formed the bond to carbon, the plus charge in carbon went away. So that's what the product would look like. I've never heard of a reaction like that, by the way, but it would be a Lewis acid-Lewis base reaction. And that's basically it for the practice exam. I can guarantee you there will be questions on acids and bases. It may or may not be this format. I can guarantee you there will be questions with Newman projections. It may or may not be this format. I can guarantee you there will be questions on cyclohexane. It may or may not be this format, but it will use those concepts for sure. Here's more acid-base questions. Here's resonance questions. Naming, formal charges. Another acid-base question. Functional groups, hybridization, it's pretty much the complete package. So I can't tell you exactly what's going to be on the exam. But I believe it's pretty spread out evenly and pretty fair. There's nothing on the exam that I believe is unfair. I don't purposely ask unfair questions. Sometimes I screw up and ask an unfair question, but I don't purposely do so. Well, there's 4 minutes left. Anyone want to see a cat?
Yes, please.
Where'd he go?
Sure. If
Sure, Barnaby.
he's
Not that he knows his name. I hear him. Here he comes. Okay, everyone wants to see you. Here's Barnaby. Oh, let me stand up a little bit.
aw, that's cute.
Yeah, he only likes me. He doesn't trust other people.
Ouch.
He looks very fluffy.
Okay, Dr. Watts, you literally hurt my feelings now. So I'm just-
Yeah, I'm sorry about that, but he doesn't trust other people. He's struggling.
it's okay. All right, thank you. Bye.
Yep. Yeah, he only trusts me.
Have a good weekend, Professor Loss.
Yep, you too. I will see you all on Monday.